On this show, we're talking about heat and network electronics. Should you mount that piece of equipment in the attic? Welcome to the show where we tackle the tough questions submitted by installers, technicians, estimators, project managers, IT personnel, and even customers. We are connecting at the human level so that we can connect the world. If you're watching this show on YouTube, would you mind hitting the subscribe button and the bell button to be notified when new content is being produced? If you're listening to us on one of the audio platforms like Stitcher or Apple or Google, would you mind leaving us a 5-star rating? Those two little steps can help us take on the algorithm and help us educate, encourage, and enrich the lives of other people in this industry. Thursday night, 6 p.m. Eastern Standard Time. What are you doing? I do a live stream on TikTok and YouTube and LinkedIn and Facebook where you get to ask your favorite RCDD your questions about design, installation, estimation, project management, even career path questions. I can hear you now, but Chuck, I'm driving my truck at 6 p.m. on Thursday nights. I don't want to get into an accident. That's okay. They are recorded and they're put on our website, letstalkcabling.com. And finally, while this show is free and will always remain free, if you like this content of this program, it's provided you some value, would you mind clicking on this QR code right here? Buy me a cup of tea, or you can even schedule a 15-minute one-on-one call with me after hours, of course, and just help support this platform. So as I mentioned, I got into a conversation recently on TikTok. It's one of my most popular ones. Somebody posted a video of them putting a piece of equipment in the attic, and I said, in a nutshell, probably not the best place to put a piece of equipment. And I quoted the half-life rule. Man, that post blew up. 85,000 views the last time I saw it. And I'll tell you what, the internet trolls came out. They were hammering me big time. That got me to thinking, maybe I'm wrong. And you know me, I'll be the first to admit when I'm wrong, and I quoted the half-life rule. For every 10 degrees above ambient temperature that a piece of equipment is exposed to, its life expectancy reduced by half. I got that from one of our webinar I attended one time, and I looked it up, and sure enough, it's out there. But you know what? I need help. I need an expert. So I went online and I did a search for heat and network equipment, and I found a magazine called Electronic Cooling, and a very interesting article which talked about the half-life rule. So I noted who the author was, and I jumped on LinkedIn, and I looked him up. We were already friends. Yeah, imagine that, the power of LinkedIn. So I shot him a request. He's a thermal engineer for a company that manufactures equipment. He's a mechanical engineer with a specialty in thermodynamics. He writes articles for electronics cooling. That's where I found him. So I asked him to come on the show, and he agreed. Welcome to the show, Ross Wilcoxon. How you doing, my friend?
Pretty good. Good to see you.
I appreciate you coming on because you might be able to help settle quite a few arguments today. And that's my hope. And before we get too much further along, could you give us just a 30-second, overview of who you are and your expertise?
Sure. Yes, Ross Wilcoxon. I'm a tech fellow at Collins Aerospace in Cedar Rapids, Iowa. We primarily make electronics that go onto airplanes. I've been here coming up on 25 years, and prior to that, I was an assistant professor of mechanical engineering at South Dakota State University. I primarily work in thermal management for electronics cooling, reliability issues. I have this side gig that sort of put you in touch with me was the fact that I'm also an editor for Electronics Cooling magazine, and I had written an article that got your attention.
Oh yes, it got my attention. And since you're designing electronics for aircraft, I'd have to imagine you have to consider everything from, I don't know what, below zero to over 150 degrees, I would imagine, right? Does that sound about right?
Well, degrees in, I can't think in Fahrenheit unless it's weather. I mean, other than that, I don't even think. So yeah, so we typically design, we've got cold start typically maybe as low as -50 C, operating ambient temperatures up into the 70s or 80s C, which I'd have to think what that is, but it's over 150 for sure, 150
Right,
Fahrenheit.
right.
So,
So the first thing I'd like for you to maybe kind of help clarify us is I already mentioned in our pre-show stuff that I did a TikTok video on somebody who's putting a PoE switch in the attic, and I mentioned that probably wasn't the best place for it since it was a non-hardened switch. And because I only mentioned the half-life rule, but there's other reasons like, dust and rodents, and I only mentioned the half-life rule. And it got me to thinking, all the people that were hammering, maybe I got the half-life rule wrong. What can you explain? What is the half-life rule?
well, the half-life rule, that you're talking about, is it says every 10 degrees C warmer the electronics are, its life is half. And the half-life rule, it's kind of like a broken clock. It's right occasionally, somewhat by accident. And so I do a lot. I'm on I review journals. I'm in conferences. So and with my magazine gig, I read a lot of papers that people submit. Right. And there seems to be this rule about 20% of papers, they seem to, on electronics cooling, they want to start with that rule, saying every 10 degree hotter, it's cutting the life in half.
Right.
And I've been in rooms where people have gotten very angry just at seeing that, because it's wrong. Okay. Although it's not always wrong.
Right.
And so I was trying to think about where it came from. And actually the oldest reference that I came across in a pretty brief review looking through it was found internally in a proposal that Collins Radio Company engineers had done in 1968.
Wow.
And I've still got a copy of that proposal. And they mentioned every 15 degrees warmer, it was a reduction in life by half. Close enough. And I think a lot of them will mention the Arrhenius equation as the basis of that. Now, the Arrhenius equation is something that is used to model a lot of chemical reactions, and it's an exponential equation. The absolute temperature is it's E to the absolute temperature divided by some constants. So exponential functions go pretty crazy when they at some point they get high. So so yeah, when things get really hot, the chemical reactions accelerate, and certain failure mechanisms within electronics are at least act like chemical reactions, so they go much faster. The thing is, when I looked at where did that number come from, and like I said, I've never found something that specifically said it, but when you look into their literature, it says the activation energy, which is one of those constants in the Arrhenius equation, reported for silicon is about 1. I don't remember the units. It's electron volts per something. I don't know. Which is kind of suspiciously convenient round number. So I don't, I've done some other things on activation energy for solder dissolution. Those numbers have this really wide range when you try to calculate it. So is it 1? Is it 2? It's in that range. It's a rough number already. And then if you look at probably in the old days when this rule first came around, silicon devices were probably typically 135 C was probably a typical max temperature that they recommended you operate things at. That's the junction temperature, not the ambient temperature.
Okay, hold on, stop right there. So this is another place where we got into huge arguments, right? Yep. Ambient temperature. Okay, what exactly is ambient temperature?
So ambient temperature is where is the heat going to you talked about in an attic, it's the air temperature in the attic. So it's where are you rejecting the heat to? Junction temperature is this nebulous little temperature. So somewhere within your device at the junction, there's some average-ish temperature that they use to calculate, we say to represent the temperature of the device. So how hot are the electronics themselves?
Right.
Okay. And 135 15 20 years ago is probably a fairly typical for industrial grade, temperatures, components. That was probably about right. So if you take the 135 degrees C as your maximum temperature, and you use that one activation energy of 1 EV, whatever it is, that sort of for silicon, and you can calculate a rate of how fast it degrades as a function of temperature. And now if you change that 135 to 145, adding 10 degrees, turns out you about double that rate. Drawing some from, this is a little bit from memory, so I have to look at my paper to see what it really is. But it's about that. So so how I interpreted it is, I think when they developed that rule of thumb that's general, but not so general, it says, if you're already running at your maximum temperature, and now you increase it by 10 degrees, expect to probably reduce your life by half.
Gotcha.
Okay, but if you're not running at that maximum temperature already, you're in a different place on that curve. And so it isn't a 2x reduction in life.
Gotcha. So I'm already wrong on two aspects already, because I quoted ambient temperature as for every 10 degrees in rise in ambient temperature, the equipment would be life expectancy would be reduced by half. So obviously I'm already wrong there.
Well, yeah, possibly. I mean, things are pretty linear. A lot of things about heat transfer are fairly linear. So if the ambient temperature goes up 10 degrees, the junction temperature will probably go up about 10 degrees, maybe. There are nuances that probably, maybe not, but yeah, it's if you're already operating right at your maximum allowable, then
right,
it should be. But the thing is, if you're at going from say 125 to 135, if you run those same equations, it's not a factor of 2. It might be more like a factor of 3.
Oh, wow.
But it's a change in what the life is, but you're already operating below your maximum temperature. So your life is longer. So I don't know, again, the numbers, I don't know what the numbers were, but just for representative, it's saying, okay, yeah, we cut, or there's some point where if you change it by 10 degrees from say 100 to 90 as your maximum, your ambient temperature. Yeah, you may cut the life by a factor of 10, but that means it's only going to survive 100 years instead of 1,000 years, according to those equations. So what I kind of argued in the paper was that, yeah, something else is going to fail before that fails. So you're no longer pushing that as your primary failure mechanism that's going to cause it to die. So no, its temperature is no longer the key driver for. So if it were only temperature, yeah, it would be even worse. But it's already lasting so long. So I don't know. It's sort of it was counterintuitive when I was first sort of learning the numbers. Then I had to think about it. But so I mean, the main point is, yeah, the rule of thumb, the half-life rule of thumb is probably not bad, but it's only if you're already running it right at the edge of its limit.
Now, would those calculations change if it was a hardened piece of equipment?
Yes, and I mean, like if it was a hardened, depending on what you mean by hardened. I mean, are you saying are the electronics?
So in the network world, you can buy hardened equipment, which instead of being cooled by internal fans, it might have a heat sink or some other type of method to help dissipate that heat.
I don't think that should have a direct impact on that. If you're thinking in terms of what your ambient temperature is, like you're saying, I'm going from my bedroom to my attic,
Right.
So like, and you're saying, oh, it's this much hotter in the attic. If you're operating with, if it's a low power system that's just operating with free convection, you don't have fins and stuff, you don't have a heat sink, you're not blowing air over it, that cooling is more, there's some temperature dependence there. so I'm thinking out loud here, but I think it's actually, if you run the numbers, it's probably actually less, or the hardened will actually more closely follow that.
Right.
That the temperatures, if you have a fan blowing over it, that fan is a primary heat transfer mechanism. If you don't have a fan, things like radiation, for example, start to have some effect.
Right.
And the radiation is so small compared to how well a fan will work that you can almost neglect it with a fan cooling. So the radiation effects will be substantially changed with the ambient temperatures. I think I'm going in circles here, and I'd have to sit there and run some numbers to feel for sure which way that I feel like it's going for sure.
Right.
But I think with the range of temperatures we're talking about, I don't think it would make a huge difference.
I did some research before our show today, and I looked up the average temperature of attics.
Mm-hmm.
And of course, it's going to vary whether you're in, Iowa or Central Florida.
Mm-hmm.
It's going to vary, but it seemed to me like the max I could find was about 130.
Okay.
So if I'm a network engineer, or if I'm a homeowner who wants to put a PoE switch in the attic, would the half-life rule be a good benchmark for figuring out my reliability of the equipment?
Hopefully in either case you're running it right at the max. If you're saying if a max worst case is 130, that's 60 degrees Fahrenheit above, say, a room, your house, probably. Roughly.
It's funny you pick up on that number, because that's exactly what they use, is 60 degrees.
And again, I have to convert that into Fahrenheit, or into civilized units of Celsius.
Right.
So that's 40 C difference, higher temperature.
Right.
You're probably getting to the point where, yeah, if you truly have a 60 degree ambient air temperature in the attic, higher than you would in the house, compared to, which is like about 40 Celsius, you're probably getting closer to that max allowable temperature,
right?
That recommended temperature, or maybe even going above it, where it would start to become important. I mean, hopefully when you're running these things, hopefully the thing is designed well enough that if you're sitting in your house, in your bedroom or whatever, or your living room or whatever, and it's 70 Fahrenheit there, it's not running right at its maximum allowable junction temperature. It's got some margin. It's probably, running 30 degrees or 40 degrees at least below what its rated temperature is. And so you're not, so temperature really shouldn't be a driver for reliability.
Gotcha. So let me ask you this. Let's say I invented a time machine. Okay. And I go out and buy me a piece of Netgear equipment. If you don't know Netgear, it's consumer grade. It's usually not really considered good quality. But the funny thing is there's a lot of Netgear equipment out there that runs for 10, 15 years. Right. It has this reputation that it can run forever. But let's say, so I put this piece of Netgear in my attic, and I run it until it just finally end of life. It finally gives up. Poof. Right. Mm-hmm. So I grab that piece of equipment. I go back in my time machine. And instead of putting my attic this time, I put it, like you mentioned, in my bedroom, 70 degrees Fahrenheit. Well, 68 if my wife has her hands on the temperature, right? And I'm able to replicate, so now it's a brand new switch again, the exact same switch. Which would last longer, the one in the 70 degree temperature, or the one that's in the 130 degree temperature?
I mean, probably there's a good chance it would be the one that's in the cooler temperatures, if that's the failure mechanism that caused it to fail in the first place. I mean, there's lots of things, I would almost bet that if something failed in the attic, I think it could be, depends on your attic a little bit too. Mine's probably got, I don't know how dusty it is in there, how much fiberglass it might be floating around there, how much wind is blowing dust around. Right. The bigger issue to me is when your ventilation holes start getting plugged. If you get some dust in there and don't allow a little bit of convection to pass through your box, now your temperature does go up, and that could have a bigger impact on temperature, or as big of impact on temperature as the fact that you're in this high ambient temperature, and the fact that maybe you're sitting it somewhere where it's you see people put these things like on a rug, on a shag rug or something.
Right,
So the
right,
stuff
right,
is
right.
going into, so those kind of issues, those are temperature derived. Those will drive the temperature related things more than as much as just as ambient at times.
Right.
I've seen that on my computer at home, and especially my son's computer one time. We pulled the cover off, and it's
Yeah.
just disgusting how much dust there is.
I was just going to say, if you've ever cracked open a case on a computer
Yeah.
that's more than 6 months old,
right,
there's a huge collection of dust in there.
Which if you've got cats, maybe you don't have your cat running around your attic, so you don't have your thing full of cat hair too. So
Right.
maybe the one in your bedroom might be worse. Things like that. So and what else is up there in the attic too? I mean, I had a few years ago we had a product that was like a repeater that went into police cars. So it went into, so they could create this network. And even though when they were out in the country and stuff, and they thought there were some thermal issues with that. So we went, and so they had, by the time I got involved, they had already said, we think we have a thermal problem. They had put a temperature sensor in the trunk of the car with this electronics, and said, yep, every day it gets hot during the day and it goes down and things. Okay. But when I started looking at the data closer, I was like, I know this doesn't look like it's ambient temperature, because it started getting hot things started warming up about 4 a.m. Not at noon, and they started cooling down about the time you get it hot. Well, turns out these guys had their shift was like from 4 a.m. to 4 p.m. and things weren't heating up so much because of the outside air temperature heating up. It was because they had this whole trunk full of electronics that were heating up the whole trunk.
Right.
So electronics tend to sort of, pollute heat to everybody else around them. And so if you have this thing squirreled away, if you have this in the attic versus if you have it in your room or something, and you have it in a kind of a closed box because you don't like the noise or something like that, or you don't want to see it, and you have it shoved in a drawer, that could be worse stuck in a drawer.
Right. Because of no ventilation. Small area gets hotter.
Yeah. So there's a lot of factors that can influence that, and temperature is just one of them.
Remember when I bought my first computer way back in 1982, was a Trash 80, Radio Shack Trash 80. And I remember in the instructions, it said that when you're not using the computer, to turn it off, don't leave it on all the time. And the reason that, and I had somebody once, and they said, well, it's because, cycling, right? Well, in an attic during the hottest part of the day might be 130, but at 2 o'clock in the morning, it might be 70 degrees, which is harder on a piece of equipment, the constant rise and fall of the temperature or a constant high temperature?
Again, probably depends on what is the mechanism that you're talking about, the failure mechanism you're talking about.
Right.
For the temperature dependent degradation of the electronics, the silicon, that's a cumulative thing based on just time at temperature. A lot of what we, one of our, the things that we kind of worry about from our systems, temperature is one environment that we have to consider, but thermal cycling is also an issue as far as like solder joint fatigue. And so when you have these components, and if you've opened up your computer lately, that computer from 1982, you probably looked at it, had a whole bunch of dip parts, and it was all kinds of nice leaded parts. Everything was there's no, they don't have those as much now, for at least for the processors. They're all flip chip, and area array parts, and so the solder joints are very, very short bumps instead of nice long leads. They don't have as much compliance. They can be more susceptible to those expansions and contractions that occur when things turn on and off and heat up and cool down. So for solder joint fatigue, it's definitely the turning thing. The temperature cycling can cause that problem. And
So the article that you wrote that kind of started this whole thing off, you mentioned in it that the failure function, heat was only one of them. What are some of the other things that could cause, or that you have to maybe plan for, or that you've seen that could cause a piece of equipment to fail? Other than cat hair, we've already mentioned cat hair. I'm assuming dog hair is okay.
probably bigger, yeah. So, I mean, again, from my perspective, it's probably different from yours. Our types of products. I mean, we're going into fairly harsh environments from a dynamics point of view, some shock and vibe. So now how much you got a big circuit board that's flipping back and forth because it's resonating. You really try to avoid that because that's really hard on solder joints. Humidity and corrosion. If you're in Florida, you probably have a different environment than you do in Nevada for something, for how much of a corrosive environment you have, for sure. I mean, salt water or salt spray
Right.
is a rough one. There's things like the cycling. If you do have temperature cycling, that solder joints have to take up that expansion and contraction of the circuit board and the parts that aren't the same, and you've got silicon that has really low expansion. But you either have other indirect factors, or like you have a plastic encapsulant on that part or on the board or whatever, and as that just fatigues due to those expansions, and now you start getting cracks, and so those cracks can either break the circuits in the circuit board, or maybe they allow moisture to get in, and now you get corrosion inside parts where you didn't expect to have it, or now that moisture gets in there and then it freezes or something, and now you have some expansion. So before my time, even, it was primarily hermetic packages, ceramic. Now it's all plastic parts, plastic packaging. So plastic tends to degrade more due to over time than ceramics. So and a lot of those are temperature driven failure modes, but they can also be exacerbated by humidity and like I said, combined with vibration. As those are probably the things that we are most thinking about. And other things, again, they sort of end up being temperature related. But if you do have you said some of these have a heat sink, and then what they, generally in this heat sinks, you put some sort of a thermal grease between the heat sink and the part, and that thermal grease, when you power things on, that generates some movement, and you actually can pump out that thermal grease, and so then over time that your heat sink isn't operating like it is, and now you get this other temperature. Now it gets too hot because of this effect. So it comes back to temperature, but not for the same reasons as a high ambient temperature.
So you mentioned about the heat and how it causes I'm a cable guy. Okay, I'm a knuckle dragging copper fiber guy who pulls cable, terminate cable. So you're gonna have to educate me here, right? So you mentioned about the heat causing the solder to expand, right?
Mm-hmm.
Wouldn't the circuit board also kind of expand and contract because of the same conditions?
Sure. Yeah, but they have different expansion coefficients.
Oh, okay.
So it's
Okay.
CTE. So like silicon has a really low thermal expansion, and circuit boards, and so silicon will typically be, again, can't remember the numbers off the top of my head, 5, 6, 7 watt parts per million per degree C. So it'll go 1 mil per 1,000 mils change in length for each degree temperature. Circuit boards, depends how much copper you have in them and things like that, but they might be 40 or 50, I think, parts per million. So, and that's why, things will bow, or, if it gets hot, sometimes things they'll have some curvature just because of that. They're trying to, because of that, those stresses as things are trying to expand at different distances because of the different thermal expansion coefficient.
That makes sense to me. See, I just assumed that they would both expand and contract at the same rate. And I thought, what's the deal if they're both expanding?
Right,
I didn't think that one's expanding more or less than the other. And I can certainly see that causing a problem, because I can see it breaking off. So let me ask you a question. Since you are, more in design of electronics and stuff, and I'm just a guy who just literally plugs them in to the outlet and plugs them into the network, right? What are some best practices that you would recommend for someone who's looking to put their network equipment to make it last a little bit longer?
Well, read the owner's manual first. See if they actually tell you what the
owner's manual.
Ambient, I know. Yeah, I know. It's in theory anyway. Yeah.
Right.
Like I do with my kids, do what I say, not what I do. So
exactly.
It's. I think I would hope most things are designed with enough margin that under normal use, temperature shouldn't be the driving issue. But try to avoid, if you can put something where it's going to be cooler, if you're putting it, especially if it's something that has a fan blowing air in it, pay attention and make sure because the more air you pull in to cool it, the more other stuff you're pulling in of dust and cat hair and things like that. And so making sure you're not preventing the cooling air from getting to it, and just so keeping the holes clean and things like that. Electronics cooling, if you're electric, because I work in this is an electronics company, right? And so I work with a lot of electrical engineers, software engineers. I half jokingly say that ME, mechanical engineer, ME stands for minority engineer here, because we are in the minority, and thermal management is just part of that. And one of the interesting quotes that Christian Bellotti he's at Microsoft now, but I heard him say something that one time that said, describe electronics cooling or thermal management is like the garbage collection of the electronics industry. We're the garbage men, right? We're getting rid of the stuff that nobody wants. And you don't move to a town because they have great garbage men, but you might move away from it if they're really, really bad. So
I was going to say, it's one of those things you don't think about until it's not working right, or you don't have
right.
it.
Yeah. And you don't have to be being a much better garbage man than the average doesn't get noticed. So as long as you're adequate, and so, it depends on the initial design. Is it, how close were you to that maximum number? And so if I know my PC or my laptop will have, I can ping it to find out what the junction temperature is. I don't know if, probably not in a lot of the equipment that you have those sort of built-in temperature sensors. If you're concerned about it, probably worth, maybe investing in you can buy a little like USB stick temperature sensors that you can put there with it, see how hot it really is getting on a bad day, and sort of monitor that is one way. And if it's over, most components, when the design of the board, a lot of commercial grade components, especially some of the small passes, the small resistors and capacitors, they'll typically just be rated for 85°C ambient temperature. And that's, and then if you're in a condition where you have higher than that, you just have to sort of show what it's doing. But that would be if this part is on a board, just sort of stuck with some ambient temperature, it doesn't get above 85. You can deal with it. So, if you're in a place where the ambient temperature in degrees C is over 85 Celsius, which I have to do that. That's What, about 180, 190,
Sounds
180
about
degrees
right.
Fahrenheit? You know, yeah, maybe you should find a different home for your router. If you're 40 degrees below, when you're at the 130, maybe that's getting where it's of some concern. And if for some reason you're sitting next to, you've got an attic you got your air conditioner in your attic and it's dumping heat into there, and you're really hot, then, and you're at the far end of um, that bell curve, then yeah,
Mhm.
maybe definitely think about
Yeah.
moving stuff.
You mentioned dust. Another question or concern I hear quite often is, we know, dust will clog up the fan and raise the heat. Is there any time dust can be conductive and may short something out?
I mean, I guess if, I suppose if it's wet or water, I mean, all of most of our circuit boards, we conformal coat them with an acrylic coating, so we're not worried about it. If it's supposed to be something used in a house, probably that's a cost adder, so it probably isn't going to be on this equipment. So I'd probably be more worried about if you have moisture condensing on the boards, then that could short things out than dust, unless your house is next to like a copper mine or something like that, where it's all copper dust.
Well, there's a lot of switch gear that gets put in. That we have industrial Ethernet, where they're putting in a lot of switches out on the plant floor to monitor, equipment, processes, and production, stuff like that. And so you're talking about a wide range of materials in industrial plants. So,
Yeah.
that's why I was thinking, because dust in your house, probably not conductive,
Right.
but maybe an
Right.
industrial plant, depending on what they're manufacturing, there's a possibility
Possible.
there. There's
Yeah.
a possibility there. So,
Yeah.
so, very cool, Ross. Very interesting conversation. I appreciate you coming
Okay.
on and shedding some light on this subject. And it sounds to me like Chuck was wrong on two fronts, and that's the whole reason I had you come
Well,
on. So,
like I said, you're right in certain circumstances, but it's not it's like any rule of thumb. What is it? All generalizations are bad, including this one, right? So you just have to kind of understand where the basis of it was.
yep.
So
Thank you, sir. I appreciate your
okay.
time.
You bet.
So, hopefully the things that you learned there are a lot of factors that can cause a piece of equipment to fail. Heat is definitely one of them. It's definitely one of them, but you got to look at the whole entire picture, as Ross said. You also probably learned that Chuck was wrong on two fronts. I was wrong on my interpretation of the half-life rule, because it's not the ambient temperature, it's the temperature of the equipment, and also ambient temperature, right? So I was using a definition from a magazine that I read one time talking about ambient temperature and being the temperature outside the room, and another temperature, room temperature, being the temperature around the equipment. So ambient temperature is right around that piece of equipment. So Chuck was wrong on two fronts. Mark that down. I'll be the first to admit when I'm wrong, right? So I hope that you learned something from the show. And if you like content like this, make sure you shoot me a message. Let me know. Until next time, knowledge is power.
That's it for this episode of today's podcast. We hope you were able to learn something. Make sure to subscribe so you don't miss out on future content. Also, leave a rating so we can help even more people learn about telecommunications. Until next time, be safe.